In the theory of algebra, complex numbers are something that are very, very useful. And I'm going to show you how to do arithmetic with complex numbers, but first I want to make sure we remember how a complex number is defined. So a complex number looks like this: a plus bi, and here a and b are real numbers, and I is what we mean by the square root of -1. Now you gotta think, okay, the square root of -1 would be the thing that multiplies by itself gives me -1. And since we know that negatives times negative are positive and positive times positives are positive, there's no real number that would multiply by itself and get -1. So this is a completely different number. Okay, now another thing is that sometimes this leads people to believe that these things don't exist. And in fact, I is called the imaginary unit. But they do exist. They do exist. They just don't get measured or counted. But in physical systems, they do show up a lot. Okay, now another part that we need to keep up with is that A here is what we call the real component, and B is called the imaginary component. Okay, and so because of this, you can imagine if B is 0, every single real number is actually a complex number. But the complex numbers are much broader than the real numbers. And again, I'm going to show you how to do 3 of our 4 operations. I'm going to show you how to add, subtract, and multiply. Alright, let's look at example A. This time I want to add 3 plus 17i plus 21 minus 5i. Addition with complex numbers is very straightforward. All I have to do is say 3 plus 21, I just add the real components, and then I add the imaginary components. So it's 17i minus 5i. And so when I do that, 3 plus 21 is 24, and 17 minus 5 is 12, so I have 12i. And that is a real number, that's a complex number, so that is our answer. Okay, B part with subtraction, it's just as simple. It's just we need to remember that when I'm subtracting, I need to distribute my negative. So I might turn this into an addition question by distributing my negative across and end up with plus 6 minus 2i. Okay, so now when I add my real parts, I have 30 and 6, which is 36. And I add I and -2i, which gives me minus I. 36 minus I is my solution. Okay, I hope those make sense. They're pretty straightforward. But now we're going to get into some multiplication. So it's not bad either. I just want to show you some details. Okay, so if I was going to multiply 2 minus x times 5 plus 3x, we would all realize that we need to use the FOIL method to do that. And that's exactly what we do here. I need to FOIL this out. So first I multiply my first term, so I have a 2 times 5. Then I multiply my outside terms, that's going to be a 2 times 3i. My inside terms, I end up with a plus 5 times -i. And then lastly, my last two terms, I have a 3i times a -i. Okay, now when I multiply that up and add it together, I end up with 10 plus 6i minus 5i. Oh, and then I end up with 3i squared. Okay, so there we did it. We can combine the 6 and -5i, but is this really a complex number? Well, if you remember what we said about I squared, we said that I equals what? The square root of -1? So then I squared has to be -1 by definition. So this is actually then 10 plus 6i minus 5i plus 3 times -1, so a minus 3. The plus 3i squared turns into a -3. Alright, so then I end up with 7 in the real component plus 1i in the imaginary component, and there it is. So when I multiply these two complex numbers, this is definitely an a plus bi situation. So this is multiplying again, but this time I want to point out something about these guys. So here I have 4 plus I and then 4 minus I. So that relationship we call complex conjugates. Complex conjugates. So when I FOIL these out, something special is going to happen. Let me show you. So when I do the first terms, I get 4 times 4. That gives me 16. My outside terms, I have 4 minus I, so it's a negative 4I. The inside terms have an I times a 4, so that's a positive 4I. And then lastly I have an I times a negative I, so I get a negative I squared. Okay, so if you notice now, my two inside terms cancel out. The negative 4I and the positive 4I subtract out. So I end up with 16 minus, what was I squared again? I squared is negative 1. Okay, so then I end up with 16 minus a negative 1, which ends up being 17. Okay, wait a minute. 17, is that a complex number? Yes, it's just my imaginary component is 0, and that's totally fine. And in fact, anytime I multiply complex conjugates like I just did here, I'll always end up with a real number. And in fact, we could have a rule that says a plus bi times a minus bi will always end up being a squared plus b squared. Okay, so let's see, is that what we did last time? I had a 4 for a and a 1 for b, right, because that's the form I had. So 4 squared is 16 plus 1 squared is 1, 17. So complex conjugates will always work this way, and they'll always bring us back in the real world. Okay, I hope this makes sense as an introduction to complex numbers and complex arithmetic. I'll show you some more examples in other videos and why we use complex numbers. And if you have any questions, please let me know. Thanks for watching.